Today, we're going to discuss the truth behind the object that broke our models and shattered scientific consensus. The interstellar visitor 3I Atlas. It slipped into the data as a whisper, a new track across the stars. Then the numbers bent. An object from between the stars, catalogued as 3I Atlas, should have been routine by now, fast, distant, hyperbolic, and forgettable. Instead, its path twitched. The predicted curve around the sun refused to hold. Observers saw a tiny, persistent shove, as if some unseen hand were nudging it off the clean geometry of gravity alone. Here's why that matters. In celestial mechanics, deviations mean physics you haven't accounted for. And when that push doesn't match dust, gas, or anything we expect from a normal comet, it's a problem. Some researchers believe this initial nudge was too precise to be purely natural. Initial estimates painted a familiar picture: faint, small, probably a dusty ice fragment or a dark asteroid. Then its course began to drift by more than the error bars allowed. The effect was subtle, millimeters per second, but relentless non-gravitational acceleration. The phrase landed with weight in mission rooms because it implied internal processes, surface jets, or something we hadn't seen before, or perhaps something we were not supposed to see. Think about that. An interstellar visitor, modified mid-flight by forces we couldn't pin down. NASA's solution team published a track fit that demanded a low-density body accelerating away from the sun. Their model needed sunlight to be doing more than warming it. It had to be shoving it. ESA's analysts disagreed. Their photometry suggested a different surface response, a higher thermal inertia, less likely to vent like a typical comet. Two major agencies, two incompatible pictures, both drawn from legitimate data. And the raw data that fueled these conflicts was quickly pulled from public servers. And this is where the room gets quiet, because space doesn't care about our confidence. As telescopes worldwide locked on, even the simple indicators refused to settle. The light curve hinted at a slow roll, then a rapid change, as if 3I Atlas altered its orientation relative to the sun. No broad, dusty tail, no textbook flare-ups near perihelion. If it was releasing anything, it wasn't behaving like normal vaporizing ice. The Joint Space Telescope pulled early spectra that were plain, almost featureless, the cosmic equivalent of a poker face. Meanwhile, tracking teams kept revising the orbit, and every revision edged the anomaly forward. Inside this rising uncertainty, a project years in the making slid into focus: the Interstellar Observation Array, a cross-agency net of sensors intended for exactly this kind of moment. The IOA's role was simple in theory, brutal in practice: turn confusion into physics, triangulate the push, map the heat, catch any faint plume that could explain the drift. But the very need for it underscored the tension. Our data pipelines, our methods, even our trust in each other were being stress-tested by a rock from nowhere. The conflict deepened with each update. NASA's brightness models implied a dark surface that would heat quickly and vent, while ESA's fit required a brighter, tougher skin that shouldn't. One side saw phantom jets. The other saw a radiation pressure effect that was too strong for the object's size. The sums didn't add up, and that's when skepticism creeped in at the edges. Were we miscalibrated? Or was 3I Atlas rewriting assumptions we didn't know we had? Some believe the two agencies were intentionally fed conflicting data from a third, undisclosed source. Observers reported a sudden change in phase behavior crossing solar longitudes where not much should happen. A surge without a tail. A pivot without a torque source we could see. The acceleration persisted, but its direction shifted slightly. Not away from the sun, not cleanly along any simple axis. If you're looking for familiar patterns, this is where they slip from your grasp. So the call went out. Stop arguing over the shadows on the wall and look for the fire. The IOA would switch to a coordinated infrared campaign to pry into the heat signatures that could betray what was happening inside. What they found next forced everyone back to the whiteboard, First, the heat map broke the rules. Then the shape did. And suddenly, empty space wasn't empty at all. The Interstellar Observation Array flipped to infrared and pulled a thermal portrait of 3I Atlas as it slid past Mars's longitude. What should have been a smooth gradient of warming became a pattern of rings and voids. Bright rims, cold cores, like a honeycomb inside a comet. Hollow zones. Not pockets of gas ready to vent, but true hollows that refused to heat the way solid material does. Here's why that matters. A normal comet warms, outgasses, loses mass, and sometimes picks up a tiny push from the jets. That would explain the odd acceleration from Part 1. But the IOA's map showed vast interior regions that weren't just cooler. They were thermally decoupled, as if heat hit a barrier and skated around it. If jets were driving the motion, we should see heat seeping from pathways to the surface. Instead, the hottest lines wrapped around cold voids that stayed stubbornly dark. NASA's first pass called it extreme porosity. Think a rubble pile, stitched together, full of gaps. ESA countered almost immediately. The emissivity was too orderly for random cavities. Their analysts flagged repeating arcs, spacing that suggested layering rather than a jumble. The IOA published both interpretations side by side, and the argument spilled into every control room. Some are convinced the repeating arcs are indicative of complex internal mechanisms. Are we seeing nature's irregularities, or a pattern that shouldn't be there? To break the tie, teams pinged it with radar. The IOA's wideband suite and partner deep space antennas sent pulses, then listened for echoes bleeding through the outer shell. The returns didn't behave like dusty rock. In certain angles, the reflections snapped into sharp, high-contrast spikes, the kind you get from smooth, coherent surfaces buried inside, and buried in those echoes was a surprise. Polarization signatures hinting at metallic crystallinity, not random metal grains. A lattice. Crystals. Think about that. Metal can crystallize in meteorites, sure, but seeing radar speculars line up with an internal thermal pattern pushed the conversation into uncomfortable territory. If those hollows are bounded by crystalline metal, you don't have a fluffy snowball. You have a structure with panels, plates, or something that acts like them. NASA urged caution. Calibration could exaggerate specular highs, and the penetration depth might be shallower than modeled. ESA leaned into the numbers. Their cross-correlation with IOA thermal ridges showed alignment within a few degrees of rotation. Meanwhile, the Joint Space Telescope team prepared a follow-up. If there's metal, spectral signatures in the near IR should back it up. But the clock was ticking. 3I Atlas was rotating fast, and the spikes came and went in seconds. Another twist. Why did the tracking data from certain ground stations seem to vanish exactly when the spikes were strongest? As the object turned, the non-gravitational push wobbled in sync with the radar glints, not with any detected dust. No plume, no visible fan. Just a subtle nudge that peaked when a reflective interior facet happened to face the sun, and faded when it turned away. If you're building a simple comet model, this is where the math starts to fray. Inside the agencies, the fault lines widened. NASA's thermal team. Sintering and collapse can make pseudo-layers, ESA's radar group. Not this coherent, not at this scale. The IOA tried to mediate with a composite. Hollow zones linked by warmer ribs, like heat was being collected and routed. A thermal network instead of a random sponge. That idea, in turn, triggered a flurry from materials scientists. A crystalline framework could move heat efficiently, concentrating energy along paths we just happened to catch in infrared. And yet, there was still the simplest objection. If it's metal, why isn't it shining invisible light? The answer came back quickly. Because the outer skin is not metal, it's coated, dark and rough. The glints are internal, seen only when radar slips between layers and bounces off something smoother below. A two-stage body, a matte shell, a reflective skeleton. Natural? Maybe. Comfortable? Not anymore. Some analysts have suggested the shell is a deliberate camouflage. The IOA's next directive was obvious. Stop staring at the skin and listen to the chemistry coming off it. Because if the interior really is that strange, the gas it releases, if any, won't smell like home. And that's when the spectra started to argue back. The first spectra were quiet, then they weren't. Lines appeared where the catalogs were blank. Here's why that matters. A normal comet off-gasses the usual suspects: water, carbon monoxide, cyanogen. Their ionized fingerprints are textbook. But the Interstellar Observation Array's ground arrays pulled down something that refused the syllabus. Ratios inverted. Unexpected charge states ion groups that looked like fragments of compounds we don't see drifting free in our neighborhood. NASA flagged an anomaly code. ESA called it premature, and the arguments began. The IOA stitched together feeds from its polar stations and mid-latitude dishes. Every pass confirmed the same thing. 3I Atlas was bleeding ions, but not in the way sunlight usually teases volatiles out of cold rock. The signatures were sharp and oddly spaced, as if coming from material that had been ordered, structured at a scale that shouldn't survive eons between the stars. The Joint Space Telescope swung in to arbitrate. It split the light with surgical precision and found spectral lines that wouldn't lock to known molecular libraries. Not just unfamiliar, misfit. Line widths too narrow for chaotic dust, energies inconsistent with simple gases, and an absorption notch that sat stubbornly between expected bands, as if a manufactured alloy were trying to tell us its composition without a Rosetta Stone. Think about that. An interstellar object, accelerating slightly without gravity's permission, now speaking in a chemical accent our labs don't recognize. Near Mars's orbit, another rule broke. As 3I Atlas crossed a brighter patch of sunlight, it didn't brighten on schedule. Its response lagged, then spiked, then plunged, like a system with a thermostat, not a snowball with a sunburn. If it were ordinary ice, heat in would mean vapor out, smooth and predictable. Instead, the energy curve doubled back on itself. ESA's photometry team called the flux non-linear albedo modulation. NASA's thermal modelers called it wrong. The IOA tried a sanity check. Polarization. Light scattered by a coma usually carries a telltale twist, alignment that shifts with angle and particle size. But the polarized signal didn't match any dust population we know. At certain phases, it rotated in the opposite direction, as if reflecting from surfaces arranged with intention. Publicly, the agencies were careful. Privately, the emails were blunt. We know now that internal memos contained the phrase active signature. Calibration error, instrument ghost, or a material our standards can't name. The Joint Space Telescope held its ground. It repeated the observation through a different grating, under different thermal loads, and the misfit lines stayed put. The IOA pinged a redundancy test, bouncing radar and cross-checking ion counts against the same region hours later. The numbers repeated, down to the stubborn notch in the spectrum. When the data refuses to change after you change everything around it, the problem is rarely the instruments. And this is where the tension really snapped. If the acceleration isn't from water jets, why aren't we seeing the expected hydrogen and hydroxyl glow? If the ions are exotic, what reservoir feeds them? And if polarization keeps hinting at order, are we looking at grains, plates, or something that cheats the word grain altogether? NASA's public line stayed conservative. Uncertain composition, further analysis required. ESA leaned bolder. Evidence for unusual material properties. The IOA, caught in the middle, published the raw streams. The scientific world watched two narratives diverge, and trust in the instruments became the protagonist. Here's the uncomfortable truth. Credibility was now the experiment. If these signals were real, the models would have to bend. If they weren't, an entire suite of telescopes had conspired to fail in the same very precise way. The investigation pivoted. Strip it back to fundamentals. If sunlight drives chemistry, follow the most basic element of all. The next step was obvious and a little terrifying. Look for hydrogen where there must be hydrogen, and see if it's missing. It wasn't there. The single most expected element. The one element you expect to find everywhere. Gone. Here's why that matters. In sunlight, ordinary comets breathe hydrogen water breaks apart, and hydrogen shouts its presence in crisp spectral lines. But when the Interstellar Observation Array swung its detectors across 3I Atlas, the map lit up with absence. Broad, clean hydrogen depletion zones carved into a body that should have been leaking the stuff. At first, that sounded impossible. Think about it. This object had already defied gravity with a tiny, stubborn push that didn't match dust or ice jets. It held hollows where solid rock should be. It carried ions no one recognized. Hydrogen should have been the easy part, the baseline check. Instead, the IOA's hydrogen overlay looked like Swiss cheese, patches of silence stitched through a region bathed in solar radiation. NASA ran the numbers twice, then a third time. Their calibration team flagged potential drift in the IOA's sensors. ESA countered with a cross-check from the Joint Space Telescope. The same slices of spectrum, the same eerie quiet where hydrogen's fingerprint should spike. Some saw systematic error. Some saw design. The data conflicts didn't melt away. They multiplied. Why was the US military running parallel, unannounced measurements during this period? Zoom in on the science. Hydrogen isn't just abundant. It's a tracer of process. If ice sublimates, you see it. If solar wind scrubs a surface, you see that too. But 3I Atlas didn't just lack hydrogen. It lacked it in patterns, concentric bands and latticed corridors where it should have pooled, almost as if something had siphoned it off or locked it down beneath layers that weren't mixing. The IOA team released a composite, infrared texture from the earlier hollows, stacked with the new hydrogen map. The layers lined up with disquieting precision. Dark rings of depletion sat on top of metallic crystalline seams identified in radar passes. That alignment is not what natural bodies usually do. Random accretion is messy. This looked ordered. Could this be an example of self-assembly at an interstellar scale? Cue the discomfort. One camp, heavy with flight engineers and instrument specialists, argued for mundane causes. Detector saturation, outgassing that fooled line ratios, a quirk in how charged grains scatter sunlight. The other camp, a coalition of material scientists and plasma chemists, pointed to engineered layering. Not necessarily intention, not necessarily technology, but a structure that selects, that blocks, that channels particles by design or by some growth regime we haven't seen. The IOA scheduled a live re-observation, this time with synchronized timestamps from NASA and ESA clocks and a parallel run on the Joint Space Telescope. The result didn't budge. Hydrogen voids persisted, sharp-edged and stable while the object rotated. If this were a plume or a holiday in the solar wind, it would smear. It didn't. It held its shape. Then a second twist. Within the depletion rings, emission from heavier radicals flickered, oxygen-bearing fragments without their partner hydrogen, carbon chains lit without the expected lighter cousins. As if the surface chemistry had been edited, selectively, with a filter that removed the simplest atom and let everything else gossip to the detectors. Publicly, agencies kept their language careful. Anomalous, non-standard, requires further validation. Privately, scientists were split. Was the IOA seeing the universe wrong? Or was it showing everyone that 3I Atlas wasn't a comet, wasn't an asteroid, and wasn't the product of any formation history we've cataloged? And then came the proposal that split the room again. Stop guessing at distance. Fly a probe past, skim the field, ping the surface, take a direct sniff, risky, expensive, necessary. If the layering was real, close-range radar and magnetometers would resolve it. If it was an illusion, the instruments would collapse the mystery into noise. They green-lit the close pass. Why was the funding approved in under 72 hours, an unprecedented speed? Next, humanity sends a machine straight into the pattern. The pass began quiet. Then the meters jumped, and the object answered. Here's why that matters. For months, distance let doubt survive. Models could disagree, instruments could be blamed. But a close pass strips away excuses. If the weirdness was illusion, a skimming probe would collapse it into normal. If it wasn't, we'd see the bones of the thing in detail. NASA navigators threaded the probe past Mars and down the narrow corridor where 3I Atlas would sweep by ESA's deep space network, locked its timing. The Interstellar Observation Array synchronized a global ping. Radar, LiDAR, and magnetometers braided into one choreographed touch. At L2, the Joint Space Telescope kept a clean spectroscopic watch, ready to catch whatever the sun's light could reveal as it scattered from the surface. The first returns built a map like no one expected to get. Not smudges, not guesswork. A high-fidelity surface, ridges traced like fingerprints, depressions that matched the hollow zones the IOA flagged weeks earlier, and a network of lines that refused to be random. Every sweep refined the geometry, driving error bars down to the point where you could argue about origins, but not about the shapes. Then came the sound. Not audible, but unmistakably coherent. A narrowband emission, phase-stable, hanging like a tone over the solar wind's static natural body's hiss. They rumble with broadband noise. 3I Atlas hummed. The probe's magnetometer spiked as it crossed a faint boundary, a skin in space we didn't know was there. Telemetry clipped, reset, came back hot. Over Earth, NASA's relay link reported transient resets. ESA's tracking station saw power ripples exactly when the tone strengthened. Across the IOA, multiple antennas wrote the same waveform into their logs down to the phase. Multiple spacecraft, multiple systems, all nudged at once. Next, the light itself begins to speak. It sharpens. The steps in brightness lock into place. Then the cadence doubles, as if the dimmer found rhythm. Here's why that matters. Comets don't blink in clean steps. Asteroids don't quantize their shine. Natural surfaces flare and fade with heat, jets, and geometry. This was discrete, intentional looking, and it rode on top of the coherent tone already whispering from the surface map. NASA's photometry team ran the numbers first. They called it relaxation oscillations. Thermal stress cracking in a material with a weird albedo. Plausible. Comforting. ESA pushed back within the hour. The steps weren't just steps. They were arranged in red, green, and near-infrared. The intervals lined up across bands. Not a color change, a pattern. Think about that. The Interstellar Observation Array did what it was built to do. Compare, compress, and correlate. Feed the light into algorithms designed for cosmic transients and terrestrial codes alike. The output wasn't a translation, but the message was clear. Random models kept losing, structured models kept winning. The Joint Space Telescope, staring in silence, added a twist. The temperature of the reflective layer barely moved during the bright pulses. Whatever was changing wasn't heat. It was geometry, or reflectivity, or both, switching on command, or under rules we don't know. Now, stack this on the earlier puzzles. Hollow zones inside the body, metallic crystalline echoes under radar, exotic ions in the wake, hydrogen oddly missing where you'd expect it most. All that, and now a light curve that refuses to behave like geology. The data conflicts surged again, not out of rivalry, but out of honest discomfort. NASA urged caution. No one wanted to announce intelligence and be wrong. ESA argued that pattern is a measurable claim. The IOA's director split the difference. We claim structure. We do not claim intent. The question of intent was immediately classified at the highest levels, so they tested structure. Prime spacings? Some fit, some didn't. Binary encodings? Maybe. The steps drifted with solar angle. They precessed with the object's slow roll, JST saw faint polarization flips synchronized with the pulses, as if flat panes were rotating in and out of view. But what panes? The high-fidelity map had hinted at tiled facets. Now time agreed, and then, just as teams converged on a workable decoder, the cadence stretched. The beat went long, the brightness smoothed. 3I Atlas did not turn. It did not break. It did not answer. It simply kept going. Behind it, a veil appeared, so thin most cameras ignored it, so stubborn the radio arrays could not, an unknown particulate residue, glitter in black space. Not loose comet dust. It polarized light like sheets, not grains. Alma's peers would have called it a frost of flakes, but the spectrometers balked. Low hydrogen signatures, odd ion pickups, a chemistry that borrowed from our table and then stepped off it. The residue drifted into a ribbon and faded with distance, leaving only a change in the way starlight scattered where it passed. Agencies filed final memos. NASA. No unambiguous encoding. YESA. Non-random temporal sequencing strongly supported. The Joint Space Telescope. Color-stable stepping consistent with controlled reflectance. The IOA, quietly, pinned a single line to the archive. If not language, it is still information. And this is where everything shifted again. The mystery didn't explode. It evaporated. The coherent tone slipped under the noise floor. The steps splayed into ordinary flicker. By the time 3I Atlas crossed the last wide circle of our watchful instruments, it was only a dim, receding point, carrying its hollows and crystals and unanswered motives back to interstellar night. It left the system unchanged in orbit, and yet nothing felt the same. Our models gained caveats. Our arguments gained humility. The Interstellar Observation Array stayed listening, not for a voice, but for structure. Because that's the legacy of 3I Atlas. A stubborn refusal to fit, a trail of silver doubt, and a sky filled with things we now know how to notice. Whether this was a probe, a remnant, or a warning, the decision is ultimately left to you.